Welcome back to the deep dive. Today we are looking at a really foundational paper in continual learning, one that I think pushed back against a lot of the growing complexity in the field.
Yeah, we're talking about Dark Experience for General Continual Learning, a strong, simple baseline by Buzzega, Boschini, and their team.
And it really gets to the heart of the matter, doesn't it? That classic stability-plasticity dilemma.
It does, but what's so compelling is how they do it. They strip away all the complex machinery, no dynamic architectures, no heavy gradient projections, and they land on something just deceptively simple.
Exactly. Which brings us to their method, Dark Experience Replay, or DER. But before we get into the nuts and bolts, we really need to set the stage with the problem they're tackling, which is General Continual Learning, GCL.
And that distinction is absolutely critical. This isn't your standard lab conditioned CL. This is meant to be the most realistic and, frankly, hostile environment for a model.
Hostile how? What makes it so different?
Well, for one, a lot of benchmarks assume you have an oracle at test time. Use something that tells the model, okay, you're being tested on task 3 now.
GCL throws that out.
Completely out.
Yeah.
And it also throws out clear task boundaries during training. The model doesn't get a signal saying task 1 is over, time to consolidate. It's just a continuous, unending stream of data.
Okay, so no task boundaries, no test time oracles. And the third constraint is the big one for any real-world application, right? The memory buffer.
Yes, the memory has to be constant. It's a fixed size. It cannot grow as you see more and more tasks.
Which immediately rules out a whole class of methods.
Oh, absolutely. Things like progressive neural networks, where you bolt on a new piece of the network for each task, that's just not viable. Your memory footprint would grow linearly, which you just can't do.
So that leaves us with two main families, regularization and rehearsal. Let's start with regularization, things like EWC. Why do they struggle in this GCL setting?
The whole idea behind EWC, elastic weight consolidation, is to figure out which weights are important for a previous task and then penalize changes to them.
Right.
But to calculate that importance, to compute the Fisher information matrix, you need to know when a task has ended. You need a stable point. In a stream without boundaries, you never get that signal.
So the very thing you need to compute is inaccessible in the problem setting.
Exactly. The Taylor expansion that underpins it, it breaks down because your parameters drift too far from where you calculated the importance. It becomes a bad approximation fast.
Okay, so regularization is a tough fit. That leaves us with rehearsal or experience replay, ER.
Yeah, and ER has often been painted as this, weak baseline, the straw man you set up just to knock down with your fancy new method.
But this paper argues that's not the case, that a simple ER with reservoir sampling is actually surprisingly strong.
Very strong. But it has a key limitation. Standard ER just stores the input, say an image X, and the ground truth label Y.
So you're reminding the network what the right answer was.
Right. But you're not reminding it of how it used to think about that input. You lose the entire functional state of the network at that point in time.
And that's the aha moment. That's where Dark Experience Replay comes in. They're capturing that state.
Precisely. They borrowed the term dark knowledge from Hinton's work on distillation. It's all about the information that's hidden in the free softmax outputs, the logits.
Okay, so let's dig into the mechanism. DER still has a fixed size buffer, populated with reservoir sampling.
Which is key, because it ensures your buffer is always an unbiased sample of everything you've seen so far without ever needing to know how long the stream is.
But instead of storing the pair XY, they store X, where Z is that raw logit vector from the network, and the objective function is then to minimize the distance between the current network's logits and those stored logits. But they use mean squared error, MSE, not KL divergence. Why is that?
Yeah, and they're very explicit about this. Softmax, by its nature, is a squashing function. It pushes one value towards 1 and everything else towards 0. You lose a ton of information about the relative relationships between the other classes.
The dark knowledge.
Exactly.
Yeah.
By matching the raw logits with MSE, you're preserving that geometry. You're telling the network, I don't just care that you thought this was a cat, I care that you thought it was more like a dog than a car.
That's a much richer signal. So there's a really subtle but powerful implication here, especially when you compare it to other distillation methods like ICRL.
Oh, it's a huge difference. ICRL waits for a task to end, gets a nice converged teacher model, and then distills from that.
It uses a perfect snapshot.
Right. But DER, because it has no boundaries, is sampling logits continuously, all throughout the messy optimization process.
Which means the buffer is full of logits from a network that was Well, not fully baked. They're suboptimal.
And that's the really counterintuitive and brilliant part. You'd think that learning from a noisy, suboptimal teacher would be a bad thing.
Yeah, that it would hurt performance.
But what they show is that matching this trajectory, these imperfect past selves, acts as an incredibly powerful regularizer. It forces the network to find solutions that are robust over time.
Which leads right into their analysis of the loss landscape and this idea of finding flat minima.
Yes, this connects to a much bigger idea in deep learning about generalization. A sharp minimum is a precarious place to be.
Because any small change to your weights, which you have to make to learn a new task, will cause a huge increase in your error on the old tasks.
That's catastrophic for getting in a nutshell. A flat minimum is like a wide, forgiving valley. You can wander around in it to learn something new without falling off a cliff for what you already knew.
And they actually measure this, right? Using the Hessian eigenvalues.
They do. They look at the trace of the Fisher information matrix as a proxy, and the results are just stark. DER and its variant find minima that are significantly flatter. They have much smaller eigenvalues than standard ER or other methods.
So those noisy logits are actually the key. They prevent the model from overconfidently settling into a sharp, task-specific solution.
It's forced to find a compromise that respects its entire history of thinking.
Okay, but there is a potential pitfall with pure DR, which they acknowledge. What happens if the data distribution shifts so dramatically that the old logits are just wrong?
If the fundamental mapping changes, relying on that old thinking could be actively harmful.
And that's where DR++ comes in.
Right. DR++ is the upgrade. It's a hybrid. It keeps the logit matching term, the distillation loss.
But it adds a second term that uses the ground truth labels, DA, that are also stored in the buffer.
Exactly. So your total loss is a mix of three things. The loss on the new data, the distillation loss in the buffer, and the standard cross-entropy loss on the buffer labels.
You've got a term for plasticity, a term for functional stability, and a term that anchors you to the ground truth.
It's a safety net. The logits preserve the structural knowledge, but the labels make sure you can correct course if that structure becomes misleading.
Let's talk results. They tested this on Cy-Far-10 Tiny ImageNet. How did it do against the state of the art?
I mean, it dominates the regularization methods like EWC and SI. That's almost a given, based on our earlier discussion. But the really interesting part is how it compares to the more complex gradient methods.
Like GEM, gradient episodic memory.
Yeah, and it outperforms GEM and AGEM. But what's even more important is the efficiency.
This is where it gets crazy. GEM is so computationally expensive.
It's unbelievable. For every single gradient update, it has to solve a quadratic programming problem. In their timing breakdown for Cy-Far-10, Dara takes about 2.5 hours to train.
Okay. And the other methods?
MER, which is meta-experience replay, took around 300 hours.
Wow. 2.5 versus 300. That's not just an improvement. That's the difference between a viable method and a theoretical curiosity.
It absolutely is. Dara is basically O1 overhead on top of normal training. It's just an MSE calculation. It's practical.
They also did an interesting analysis on model calibration.
Right, the expected calibration error, or ECE. We know modern networks can be wildly overconfident.
And DR helps with that.
Significantly. By distilling those soft targets, the student learns to inherit the teacher's uncertainty. Hard labels from cross-entropy push the model to be certain, but the logits temper that, leading to a much better calibrated model without any post-hoc tricks.
I also loved the buffer informativeness experiment. That felt really clever.
It was. They asked a simple question. If you could only learn from what's in the buffer, which buffer is better?
So they train a fresh network on just the ER buffer, the images and label.
And another fresh network on just the DR buffer, the images and the stored logits.
And the one trained on the logits performs better.
Much better. It's empirical proof that the logit vector Z is just a higher bandwidth signal. It contains more useful information about the data distribution than the one hot label Y.
Okay, so to really push this idea of general CL, they even introduced a new benchmark.
Yeah, MMI is 360.
What's the setup there?
It's designed to be a nightmare scenario. You get batches of 2 digits at a time, say zeros and ones. But throughout the stream, the images are slowly, continuously rotating.
Okay, so that's a gradual drift.
Exactly. And then, every so often, the pair of digits suddenly changes. You go from 0, 1 to 1, 2.
So you have gradual and abrupt shifts happening at the same time.
And methods that rely on detecting a boundary or assuming some kind of stability just fall apart. And DR plus just, they handle it beautifully. A huge performance gap opens up.
It really validates the whole approach, so you don't need to know when things change, you just need to stay consistent with your past.
The consistency is the key.
So to wrap this up, what are the big takeaways? We have a method that's algorithmically simple, computationally cheap.
And it sets a new state-of-the-art for this very difficult, very realistic GCL setting.
The first key takeaway for me is that storing logits is just more sample efficient. It's a richer memory.
For sure. And the second is that matching the entire optimization trajectory, even the imperfect parts, is what gets you to these robust, flat minima.
It's a paradigm shift, really. It's not about freezing weights. It's about preserving the network's function.
Right. And it just raises the bar for the whole field. If you're going to propose a complex new method now, it has to be better and more efficient than a simple buffer with an MSE loss.
A really compelling and elegant piece of work. It almost leaves you with this idea that maybe perfect, crystal clear memories aren't what we need for flexible learning. Maybe it's the imperfect, messy, suboptimal memories that are the real key to adaptation.
That's a great way to put it. The journey is more important than the destination.
We'll link the paper in the show notes for anyone who wants to go deeper. For now, that's all for this deep dive. Thanks for listening.